So, good morning. Today, we're going to be jumping in, looking at solid liquid systems, as well as liquid-liquid equilibrium and systems involving multiple liquid phases. As we kind of move towards wrapping up Chapter 6, as well as the course material here focused on material balance calculations. So we touched base on this a little bit at the end of yesterday's lecture, looking at solid liquid systems and how we consider them in terms of material balances. And one of the things that we were looking at is crystallization from saturated solutions, and being one of the most common ways in which we achieve solid liquid separation, where often we have a saturated solution and it's going to be solid in the liquid phase. It goes through a crystallizer, where then you can have solid crystals and less of a saturated solution. And sometimes you'll see the solvent being removed, so solvent removal, but not always. And then the system will be moved through a filtration step. Where in the filtration, you're going to have some sort of filtrate, which is the saturated solution that can pass through the filter. So I'm going to say this is M1, M2, M3, M4. And then with what's remained is, what gets retained by the filter. A lot of times it's referred to as a filter cake, which, depending on the nature, sometimes this process will end here, but oftentimes you might see it moved through a dryer, which removes the solid crystals in that cake from your solvent. So a lot of times, one of the key things you want to keep in mind are material balances involving the solid, material balances on your solvent, and don't underestimate the utility of overall material balances. Often, if things associated with the product are specified, that allows you to do some additional calculation to solve for some of the streams within the process. So let's look at an example of crystallization, assuming I have a 150 kilogram saturated solution of silver nitrate, in water at 100 degrees C. So this solution is going to be cooled to 20 degrees C to form crystals of silver nitrate. So this system is saturated at 100 C. It gets cooled such that the saturation concentration falls, which results in solid crystals being formed. So the crystals are filtered from the slurry, which results in a filter cake. That is, I believe, 80% solid crystals and 20 weight, and I'm going to say weight percent to be more specific, and feel free to ask me those kinds of things. If I say percent, to be like solid weight percent, mole percent, saturated solution, which means there's a little bit of solution trapped in that cake. And so this cake moves through a dryer, which removes the remaining solvent. So let's see if we can calculate the mass of dry crystals So as always, I definitely recommend you draw the process out. So we have a cooler or heat exchanger, a filter, and then we have our dryer. From the problem, we know we have 150 kilograms of saturated solution, and it's at 100 degrees C. So how do we find information associated with this process? Well, I'll quickly finish this drawing. We know the filter has some filtrate, and then some cake continues. And the dryer has just water being separated from dry crystals. And so for this propolis, at 100 degrees C, the solubility of silver nitrate is approximately 952 grams of silver nitrate per 100 grams of water. Let me clean that up. This pen gets a little wonky sometimes. And at 20 degrees C, the solubility falls to 222 grams of silver nitrate per 100 grams of water. So since I'm looking at these systems and I have saturated solution both entering and leaving that cooling, I'll call it a cooling crystallizer. I can estimate the weight fraction of silver nitrate and water knowing it's a saturated solution. So since the solubility is 952 out of 100, that tells me that the weight fraction of silver nitrate would be on the order of 952 divided by 100 plus 952. Meaning if I had a saturated solution of 952 grams of silver nitrate in 100 grams of water, then the fraction of silver nitrate would be 952 over 100 grams plus 952, or about 0.905 grams of silver nitrate per gram of solution, which I like to call SOL apostrophe N. So the weight fractions in this, 0.905 silver nitrate and 0.095 water. So if I'm going to label these streams, and kind of just to keep track of things, I'm going to call this stream M1. This can be M2, M3, M4, M5, and M6. So M1 equals 150 kilograms. And I didn't have a time basis, so I guess technically they don't have dots, but just depending on how picky you want to be in notation. And so the silver nitrate in M1 is 0.905 times 150 kilograms. Which is 135.75. So we know we have that much silver nitrate entering the process. And the amount of water is just 150 minus that, or 14.25 kilograms of water. It's always good to know if you can get that input to help you kind of balance things out when you look at overall systems. So with that in mind, if this system's at 100 degrees C and it falls to 20 degrees C when it leaves, the mole fraction in that saturated solution should be, using that same method, 222 grams of silver nitrate over 100 grams plus 222. Or about 0.689 grams of silver nitrate per gram of solution. So if I start looking at the M2 stream, I have 0.689 grams of silver nitrate per gram of solution. That implies that I have approximately 0.311 grams of water per grams of solution. So if I'd look at a balance of water on the crystallizer, I can say, well, the mass in equals the mass out. It's a steady state process, meaning if I have about 14.25 kilograms coming in, that's how much I have to have coming out. And if the water makes up 0.311 grams of that saturated solution, then the mass of the saturated solution in 2 should equal 14.25 divided by 0.311. Or 45.89 kilograms. So that's the mass of the total, the total mass of the saturated solution.
I have a question.
Yes.
If you did that on the silver, it would be 197. So what made you use the water?
Well, I use the water because the water's only in solution. The silver gets separated into part of the solution and then pure crystals outside of that solution.
Okay.
Because we're looking at 2 phases now on the outlet of the crystallizer, a liquid phase and a solid phase.
So you don't just have pure silver and pure water coming out of the
No,
first
you
cluster.
have pure silver crystals and then a solution of silver in water crystals, in water.
Okay.
And so knowing the water isn't forming a solid, I can look at a balance on the water to get the total mass of the solution. And then from that, what we can do now is look at a balance of the silver nitrate on the crystallizer. And say, well, if the total mass of the saturated solution is 45.89 kilograms, then the mass of silver nitrate, and I know these notations aren't helpful, in the saturated solution should be that 45.85 kilograms times 0.689. Or 31.62. And that's of silver nitrate in solution. And so since we had already stated there's 135.7 kilograms of silver nitrate coming in, the remainder must be dry crystals. And so the amount of dry crystals is the 135.75 kilograms minus 31.62, or 104.13 kilograms of silver nitrate crystals. So now I know how much I had out of that crystallizer as crystals and how much silver nitrate is still in solution. So as I do these things, I like to kind of come back and fill in with a different color. So I've got, how much did I have solid? 104.13, I think. 104.13 kilograms. And the solution was 45.89 of solution. See if I can zoom in. Make this a little neater. 4.13 kilograms, 45.89 kilograms. And of the solution, it's 0.689 silver nitrate and 0.311 water. And this is at, was it 20 degrees? Yes, 20 degrees. And so now I have that information associated with what came into the crystallizer and what left. And so now I can look at the filter. And looking at the problem, it said the filter system filters the majority of the solution from the dry crystals. However, the cake that remains is 80 weight % solid crystals and 20 weight % saturated solution. So if I look at a balance on the filter, and I have 80 weight % of the cake is the saturated solution, excuse me, is dry crystals, and 20% is the solution, then the mass of that cake, which is what I should be M3, is the mass of the dry crystals divided by 0.8, which the mass of the dry crystals was 104.13 kilograms. So the mass of the total cake is about 130.16 kilograms. And that tells me that 130.16 minus 104.13 is the amount of saturated solution in the cake. So saturated solution. So now I know how much saturation solution is in the cake. And so to find M4, I can look at a balance of solution on the filter process and say if 26 kilograms is stuck in the cake, the rest must have been successfully filtered. And my saturated solution was about 45.89 kilograms. So my filtrate M4 is 45.89 kilograms minus what's entrained in the cake, or 26.03 kilograms. Or 19.86 kilograms saturated solution. So I can put that in here if I'd like, saying this is 19.85. This is about 130.16 kilograms. And so now I'm left with finding if the amount of dry crystals and water leaving the process. So now I'm going to look at balances on my dryer. And I'm a little far down, so I'm going to just draw it again here. Never hurts to have a bunch of drawings. So this is M4, this is M5, or excuse me, this I had labeled as M5, I want to be consistent. And we have M6. So I had 130.16 kilograms coming in. Of that, I had about 104.13 kilograms of crystals. And the rest being the solution, or 26.03. So the question is, how do I find the amount of dry crystals leaving the process in the dryer? Well, if all the water gets removed, if I know how much water is leaving, I can find the amount of dry crystals. And since we knew the solubility, we know the breakdown of concentration in that saturated solution, right? Because at that saturated solution, I know that it was about 0.689 kilograms per kilograms crystals, or silver nitrate, I should say, and only 0.311 kilograms per kilogram water. So the amount of water, if water enters only in M4 and leaves only in M6, the amount of water removed would be the 26.03 kilograms in that solution times 0.311, or 8.09 kilograms of water, which means the remainder, or the actual crystals in that solution, eventually falls out and joins, and it all becomes dry crystals in the process, or 26.03 times 0.689, which gets added to the amount of dry crystals, or 122.1 kilograms of dry crystals. So that tells us how much dry silver nitrate crystals we produced. And looking back on our process, we had about 135.75 kilograms of dry crystals, so the yield's pretty high. Is there any questions on that problem? It's a little complex in terms of the material balances, but if you just kind of take it one step at a time, try to stay organized, I believe you will all do well on these types of problems. So let's look at one more problem. So let's say I have a solution of potassium nitrate in water, and I'm going to put in 100 kilograms per hour into a crystallizer. And currently this solution's at 80 degrees Celsius, and my output, because my crystallizer's operating at 40 degrees Celsius. So what I'm going to end up with is a saturated solution and dry crystals. And currently, this is being fed with 60 weight percent KNO3 and 40 weight percent water. So the question is, at what temperature does the first crystal form? Well, how are we going to find that? Well, we need to know, based off this input, what's going to be the temperature where the solubility of KNO3 equals the concentration in this feed solution. Well, in section 6.5 of the text, there should be a figure that shows solubility of some salts, including KNO3, versus temperature. And actually, if you guys would like, I can try to pull it up for you, because I am fortunate to have been provided with a digital copy of the book. Better late than never, right? So, let me turn to the right page. So you guys, can you guys see my entire screen? So we have this chart here within the book, and we see we have the solubility as a function of temperature. And so right now it's coming in at about 80, and it's going to fall to 40. So we can see the extent that the solubility is going to fall. But to find the temperature in which the first crystals form, we have to determine what we're really looking for is the temperature which the saturated solution or the solubility is equal to that in the feed. So we need to get the feed in this grams per 100 grams format. And so I know I've got, if I have 100 kilograms per hour with 68% KNO3, that means I have 60 kilograms KNO3 and 40 kilograms water. And if I multiply these by 2.5, then I have 100 kilograms water to 150 kilograms KNO3, keeping those ratios the same. Meaning this concentration is 150 kilograms per 100 kilograms water. So if I jump back to my chart, that 150 kilograms per gram or kilogram is right here. So the first crystal should start to form at this intersection point here, which, looking at it, is about 75 degrees C. So based on the graph, crystals start to form at approximately 75 degrees Celsius. Meaning, as I continue on this, cooling it to 40, more and more crystals will fall. And if it's at 40 degrees Celsius, the saturated solution falls to about 60 kilograms of potassium nitrate per kilogram water. So if I know at 40 degrees Celsius, the solubility is about 60 kilograms silver nitrate per 100 kilograms water. That tells me the weight fraction in that saturated solution of crystals. It would just be 60 over 160, or about 0.375 kilograms per kilograms potassium nitrate and 0.625 kilograms per kilogram water. So I have 0.375 potassium nitrate and 0.625 water in that saturated solution leaving the crystallizer. So if I did a water balance, on the crystallizer, and I labeled my streams properly, M1, M2, M3, I would have 0.4 M1 is equal to 0.625 M2, because the water is leaving only an M2, not an M1, and N equals out for this balance. So I have 40 kilograms, which is water, equals 0.625 of M2, which tells me M2 is about 64 kilograms per hour. So I have 64 kilograms per hour, leaving a saturated solution. If this is the water leaving at 40 kilograms per hour, which tells me that I should have 24 kilograms per hour of crystals in that saturated solution. And doing a material balance of crystals, or potassium nitrate balance, I have M1 equals M2 plus M3, or 0.6, 375. So if I have 60 kilograms here per hour, 20 kilograms per hour here, that tells us how much M3 is, which is just 60 kilograms per hour minus 24 kilograms per hour, which is 36 kilograms per hour. So in this process, I'm producing 36 kilograms per hour of dry potassium nitrate crystals. All right. Anything I can state to clarify? Are you guys comfortable with those types of material balance problems, and do you feel confident that you could do those calculations on a homework set and or the final? Is there anything I can do to clarify or reemphasize? No? Okay. One last thing to mention when looking at solid liquid systems is that of colligative properties. And essentially, a colligative property is a physical property of a solution that changes due to the presence of a solute. But it's largely independent of the solute's properties. Which means that the solvent and solution properties are changing because there's a solute present, not necessarily because what the solute is. And the common ways, properties that are considered colligative are vapor pressure, boiling point, and melting points. The presence of solvents, or excuse me, solutes within a solvent causes these values to fluctuate. And so what we have is vapor pressure lowering, boiling point elevation, and melting point lowering. And what that tells us is that the vapor pressure of a solvent in a solution is lower due to the presence of dissolved solids. And so we can calculate the effective vapor pressure of a solution, or P star E, as 1 minus X of P star naught, where P star naught would be the vapor pressure without any solute present. These are both functions of temperature. And X is the mole fraction, or excuse me, the weight fraction. Let me make sure it's weight fraction. I don't want to tell you wrong. It is mole fraction. I would say that didn't seem right, probably. Of the solute. And so what that means is the amount of solute lowers our vapor pressure. And there are similar expressions for changes in boiling point, where the boiling point of a solution is equal to the boiling point without the solution, or as a pure solvent, plus R times the boiling point normal over the enthalpy of vaporization times the mole fraction of our solute. And the melting point changes is the normal melting point minus RT squared over delta H m times X, where this delta H sub B is the enthalpy of vaporization of your solvent, and delta H sub m is the enthalpy of fusion of your solvent. So your boiling point increases, your melting point is lowered.
What do you mean by P star not in vapor pressure?
That would be the normal vapor pressure you would calculate, like using Antoine's. That would be the vapor pressure of the pure solvent.
Of the solvent?
Yeah.
All right.
So yeah, we can look at a quick example. So if I have 5 grams of a solute and 100 grams of water at 1 atm, and I slowly heat the solution, and the water begins to boil at about 100.421 degrees Celsius. Don't ask me how they got a thermocouple that precise, but apparently they spent a lot of money. And so let's estimate the molecular weight of the solute. So we're looking at something in water. When we heat the solution, we notice that the water boils at 100.421 degrees Celsius. We would like to see if we can estimate the molecular weight of the solute. Well, from the expression I gave above, the boiling point is equal to the normal boiling point plus R, which is ideal gas constants, times the boiling point squared over the enthalpy of vaporization times the mole fraction of that solute. And if I rearrange this, I can say the elevated boiling point minus the normal boiling point, or the delta, the change in the boiling point, is simply equal to this term here. So the boiling point measured was 100.421 degrees Celsius. The normal boiling point for water at 1 atmosphere is 100 degrees C. So I am left with 0.421 degrees Celsius equals R TB naught squared over delta H sub V times X. Well, the enthalpy of vaporization from water is approximately 40,656 joules per mole. R is 8.314 joules per mole Kelvin. And we already said what the normal boiling point of water is, 100 degrees C, or 373 Kelvin. So what we can do is use this expression to solve for a mole fraction. Or I can say 0.421 degrees Celsius is equal to 8.314 joules per mole Kelvin. Times 373 Kelvin divided by, Kelvin squared, divided by the enthalpy of vaporization, 40,656 joules per mole, times X. And so if you solve for X, you get about 0.015. So with that mole fraction, if X equals the moles of our solute over the total moles, I can say, well, the mass of the solute over the molecular weight is the moles of solute divided by the mass of solute over the molecular weight plus the mass of water over the molecular weight of water. So it's a little ugly in its writing, but I would write it as 0.015 equals 5 grams over the molecular weight we're looking for, divided by 5 grams over the molecular weight we're looking for, plus the mass of water, which was 100 grams, over the molecular weight of water, which is 18 grams per mole. So then if you solve for the molecular weight, you get about 60 grams per mole. All right. I think that's probably a really good place to stop. Would you guys want me to work a little bit more and talk about liquid equilibrium now, or do you want me to go ahead and we can just talk about finishing up that last sections tomorrow while we work some problems? I'll let you guys tell me what you would prefer. Good talk. All right. Well, then we'll go ahead and look at ternary diagrams tomorrow and liquid equilibrium, which should wrap up chapter 6 in the course. We might touch base on absorption or solid absorption, or I might just omit it for now. But I'll take a look at the homeworks and the final and decide tomorrow whether we should discuss it or not. But if that's all we've got today, I'll be on this afternoon to answer questions about the homework. Don't forget to work on the case study because, yeah, it's takes a little bit of time, as I'm sure many of you guys are aware of, and I want to make sure that nobody has to do a crunch, and I want you all to do well. And then, as I always say, focus more on getting the material flow rates. Don't worry too much about the temperature and pressure. Just really get that stream table associated with all the flows figured out. I'm really not going to look too terribly carefully at temperatures and pressures. I think those calculations are going to be better suited when you're looking at 308, when you start looking at energy balancing. That's the best place to do that. As I know you guys have freaked out a little bit about the like that compressor calculation. Don't worry about that stuff. Just if you could get the material balances done, write the report based on those, I will be happy and I will award full credit. Okay? Hopefully that'll make y'all feel a little bit better. But thank you all for being in attendance, and have a great day.